Okay, so welcome to the 8th lecture, and today we finally leave the space of graph minors. I know finally, but we leave the space of graph minors, and we're looking at another very vivid and very wide topic in graph theory, namely colorings and coloring graphs, and particularly coloring planar graphs here. Okay, and this is the topic of today's lecture. And just, this is the definition that probably all of you have seen, but if you have a graph, let's make a graph like if you have a graph, say this graph, okay, by coloring the graph, proper coloring the graph, we mean that we are assigning to vertices different colors. They're usually integers, but sometimes there'll be different set. It doesn't really matter what's exactly the set of colors used, whether they are integers or some different objects. Like the number of different colors, the number of different objects really counts. But we are going to assign colors to the vertices in such a way that the neighboring guys need to receive different colors. So we are allowed to color these two guys blue, but we need to use different colors like red and gray for these two guys. And yeah, so we need 3 colors on this graph, and 3 colors suffice. And this is how this is what proper coloring, and everybody probably have seen at some moment such a definition. And the chromatic number is the minimum number of colors needed. And this is really what we are interested in. We're not really interested in what's exactly the names of the colors or integers, words, letters, or whatever. We're interested in what's the minimum number of colors you need to use to color a graph. And this is quite a very strange graph invariant in the sense that it's really hard to understand what's the chromatic number of a graph. If you think about okay, graphs with chromatic number 0 is the empty graph, the chromatic number 1 are edgeless graphs, chromatic number 2 are bipartite graphs. Yes, so those are the guys that you can partition to left and right. The 2 colors are left and right, so that they just go on across. And it's easy to check whether the graph is bipartite because this coloring just propagates for every connected component. But what you can learn, for example, the algorithmic course, but also in many other probably places, is that checking if you can free color graph, this is a hard problem. So they're not supposed here to discuss too much algorithm, but it means also from the combinatorics point of view that you shouldn't expect a nice characteristic when a graph is free colorable. Yeah? Because if something is hard, you shouldn't expect the problem to be in co-NP, so you don't expect the problem to have a nice characterization of non-free colorable graphs. That non-free colorable is somehow vicious, so we can actually describe the free color graphs by showing the coloring, but you shouldn't be able to easily prove that the graph is not free colorable. So there shouldn't be a good way of studying these graphs. Yeah, so this should be difficult in general. And also, if you think in general, this is not really on the slide. Even approximating chromatic number is very difficult. So, between big chromatic number and super big chromatic number, this is also difficult. So this is a very complicated and hard to understand graph parameter, but you can make it even more complicated. So instead of looking at the chromatic number, there's also a notion which would be important today, slightly more general one, namely least coloring. So this comes from, at least in my head, it comes from the intuition that if you start doing some branching algorithms or trying to color a graph, you assign some vertices some colors, and then the neighbors, if you assign to a vertex some color, you make the vertex gray, then if you look at all the neighboring guys, these guys cannot be gray any longer. They're not gray. They can't be gray any longer. So you can think of every guy really having a list, every guy having a list of still allowed colors. And the question is and now, coloring this guy gray, deletes the gray color from all the neighbors. And then every vertex tries to pick a guy from the list, and we try to solve this instance. And this comes from when you are doing proper coloring, everybody starts with the same list of all available colors, and then you're trying to and then somehow some sort of process tries to assign the colors. But you can also think of starting even with from every vertex having a very different list, or very different list, and then every guy chooses his color from his list, and he needs to be different than his neighbors in his choice. Okay, so that's list coloring. So every guy has got a list of colors, and the lists can vary up there. And it turns out that sometimes you can express a bit different things here. Okay, so there's a notion of choosability, or least chromatic number, this is also called least chromatic number, is that is the number, I mean, we say that the graph is k choosable, or like the least chromatic number is at most k, if every guy gets a list of at most k elements, then you can choose the coloring. Okay, so the graph was k colorable if every guy gets a list of 1 from 1 to k, like the same list of k elements, then it's k colorable. And now you are quantifying more, so requiring more that whatever list the guys get, I mean, you will find the k coloring. Okay, so it feels like, hey, I mean, if the lists are different between each other, it may be even easier to find the k coloring. Like it feels like at the beginning that getting the same list is like the worst case because they're too much convicts, but it's not true. I mean, so let's just look at the following example. Let's look at the example of a graph, of a bipartite graph. So this is like a 2 colorable graph, but let's do a strange lists. So let's make a graph which has got k vertices on one side, okay, and a lot of vertices on the other side. Namely, for every function from k to k, there's a vertex on the left. There's a vertex WF. So there's a lot of vertices on the other side. Okay, and this is a full bipartite graph. And trick is within the lists. So let's change the color to blue, and let's think of the palette of colors as a k by k grid. I mean, k by k grid. So the palette is k by k. Okay, and every vertex here, vi, gets just the ith row as his list. So this is v1's list. This is v2's lists, etc. So they're like a list of the vertex on the left is just a row in this like k by k grid. Okay, but if you look at the guy on the right, the guy has a function from k to k, and this function chooses like which guy from each row you have in the list. So this function says that, okay, I have got 1f of 1 here, 2f of 2, 3f of 3, like this function f says like for every choice of one vertex from the row, you get a vertex on the right that has exactly this choice. Okay, that has exactly this choice. And so, okay, so this is the construction, and now let's try to make a coloring with this list. So every guy has a list of size k, okay, but let's take pink, let's take magenta color and make a coloring. So now every guy here chooses one color from his list, so choose one list from his row. Okay, and well, okay, that's fine. But now there's this very specific guy on the right that has got exactly this function, what this guy on the left chose, and he has got no color left. Okay, and whatever you do on the left, there's exactly one guy on the right that you exactly hit his colors, because I mean, for every choice of the colors on the left, there's a guy with exactly this colors as his list. Okay, so this example shows that you can make this example like in many different similar fashion, but this example shows that, I mean, there are graphs that are 2 colorable. I mean, this is a bipartite graph where, like, I mean, you can pump up in the bipartite graphs the choosability as much as you want. I mean, by taking larger and larger examples of this type. Okay, so yeah, so this is like this an example that this notion of choosability and least color and normal chromatic number diverge sometimes. And
I have a question.
Yes.
Can you say what's the size of the lists of these vertices on the right? How many vertices?
They're exactly k, because you get from, I mean, there's this vertex of the rest is like for every row, you get one element. So the size is exactly k on the right.
Okay, thanks.
Yeah. Okay, this is why we chose like k by k grid, like because the number of columns is the list on the left and the number of rows is the list on the right. Okay. Good. So this is yeah. So this is example where this differ, and we'll study both variants. I mean, they're sometimes, I mean, interesting on their own. Okay. So we are going for planar graphs, and planar graphs are famous because of something called the 4-color theorem. Maybe like that there was a conjecture for a very long time that planar graphs are 4-colorable, and there were actually a number of fake proofs in the 19th century of this fact, when this fact was formalized in there, that were like fake or incorrect proofs that this is their 4-colorable, and this turned out to be true. It was first proven by Appel and Haken in the 70s, but it was proved with small asterisk, in the sense that there was a proof that used a lot of computer-assisted case analysis, And it wasn't completely trusted. I mean, in the sense that there were a lot of small details, a lot of like tiny fishy places, and it was not really proof. To the point that one of the a few people, Robertson, Sanders, Seymour, and Thomas, actually tried to understand this proof and verify it, and they failed. If you read and they published a paper in 1994 that is essentially a revised proof of Appel and Haken, like simplified and revised proof of Appel and Haken. That is like that they try. I mean, they show it at this. Okay, this is a new proof of the four-color theorem. It's actually built on the previous one. It's a simplified proof of Appel and Haken, but with all the things ironed out. And yeah, they say, okay, now we see that this is correct. Okay, so I mean, you can think about. I mean. Usually in this literature, we cite Appel and Haken as like the guys that proved the four-color theorem because their proof was more or less correct, or I mean, there were a few things we don't completely understand, or like there were some cases that were not completely like. I mean, in the sense that it was very hard to verify a lot of cases. Maybe let's say it this way. But building on their ideas and building on their approach, Robertson, Sanders, and Seymour in 1994 like provided like a simplified, cleaned proof without any like fish places up there. Okay, it was still a computer assisted, so the number of cases was less, but it was still computer assisted. There's still a number of cases. Like there's a few hundred of cases that just at the end needs to be checked by a computer. Okay, we will see today the proof that planar graphs are 5-colorable. This is easy, and we will see some insight into how does this proofs work to understand that it was there. My intuition about the four-color theorem is that it's an accident. So in the sense that there is an excellent reason why planar graphs are 5-colorable. Actually, we see that the planar graphs are 5 choosable today. And the fact that this is you can go down to 4 is sort of an accident. That actually all these cases you can hammer down, and in the end it's 4-color is like a very boundary thing. I mean, very like stepping on a thin line here. And I don't feel there's a really deep combinatorial reason why 4 colors suffice. Okay, so that is my understanding here, but we'll see what are the techniques needed. The techniques needed here are somewhat interesting. If we see something, right? There's an obvious remark here that actually, I mean, 4 colors is the best you can hope for because the 4 vertex clique is a planar graph and it needs 4 colors. Yeah, so that's it. The other thing we'll see today is the proof of Thomas Sen from 1994. It was actually a conjecture. I mean, okay, the choosability was a concept defined much later than colorability of graph, but there was a conjecture for a long while whether planar graphs are 5 choosable. There are clearly 6 choosable. We'll discuss it in a moment, but about 5 choosability of the graphs and what's actually the choosability of planar graphs. And there's a very beautiful, a very short proof of Thomas Sen we'll see today that planar graphs are 5 choosable actually. And there is a matching example, which is way more complicated than K4. I decided it's not make sense to discuss it here in details because it's actually like a few page construction with analysis of a planar graph that is not 4 choosable. So the 5 is optimal here. I mean, yeah. So there are planar graphs that are not 4 choosable. You can Google up the example and read it. I mean, it's working example that, I mean, you can study it, but I didn't find it super insightful. Okay, so that's the status here, and this is the things we're going to discuss today. And the starting point for the discussion is the Euler's formula that everybody knows, but let us recall. If I have got the connected graph, let's try connected plane graph. So like a plane graph is a graph embedded on a plane, already like with an embedding. So we've got a plane graph like that, okay? And now what I see, I mean, I can count the number of vertices. So here in this picture, the number of vertices is 8. The number of edges is 4, 7, 10, I think 11. And now let's count the faces. Let's take the grip and count the faces. I have got these faces inside. So the faces are like the connected, maximal connected regions of a plane after you delete the graph. 1, 2, 3, 4. And the outside is also a face. This is the outer face. Okay, so the number of faces is 5. And the number of edges was 11. What I did here. Yeah, the number of edges was 11 for here. Yeah, the number of edges was 11. And now you can say, I mean, that number of vertices plus the number of faces minus number of edges is 2. And this is for all connected planar graphs. And you can easily prove it by taking a rubber. Okay, I'm taking a rubber here and saying here in this picture, well, okay, if this graph is not a forest, then I can find a cycle, like for example, this cycle here, and wipe out one edge. So I'm wiping out one edge. And okay, so maybe we should just actually see what's going on here. So I'm wiping out edge. And by wiping one edge on a cycle, I'm decreasing the number of faces by one, and I'm decreasing the number of edges by one. Okay, this is wiping an edge on a file. I delete each on a cycle. Okay, and once you can no longer do this, you get a forest. And in a forest, you can delete a degree 1 vertex. Okay, if you delete a degree 1 vertex, delete your degree 1 vertex, then the number of faces stays the same, the number of edges drops by 1, and the number of vertices drops by 1. Okay, and after this process ends, you end up with 1 vertex. So you end up with 1 vertex, 1 face, and 0 edges. And the formula is satisfied here. And in all the steps on the way there, you decrease like one of these things by 1, and you decrease number of edges by 1. So by induction, the formula is satisfied. Okay, that wasn't rocket science, but this is a very important statement here. So we have proved Euler's formula on planar graphs here. Okay, and now let's go to the first corollary of Euler's formula, namely that if you have a planar graph, which is a simple graph, so you don't have, so the Euler's formula also works if you have multiple edges. I mean, you just wipe out one of these edges, and the number of edges and faces decreases by 1 because you treat this in between also as a face. Okay, but if you look at the planar graph that doesn't contain multiple edges and loops, so a simple planar graph, then the minimum degree needs to be at most 5. Okay, and this is a fact that also most of you probably have seen. But I want to show you 2 proofs of it. It's like the second proof will be insightful, but let's make first the first proof, and this is the proof that probably most of you already seen. And okay, let's count the edges in 2 ways. First, I mean, count the edges, like every face counts edges around it. Okay, so so every edge will be counted twice because on edge you have got face on both sides, and every face will count at least 3 edges because we have a simple graph. So every face has got size at least 3. So every face counts at least 3 edges, and every edge is counted twice, which means that, okay, this is the lower bound on how many faces will count, and this is what will be the total count for all faces. So we've got this inequality. Okay, and now just recall the Euler's formula: n plus f minus m equals 2. So now we want to get rid of f. So now we say, okay, so f is at most 2/3 m. So we say, okay, so this is at most n minus 1/3 m. Okay, so if we change the things, we have got that 3n minus 6 is larger than m. Okay, as up there. So now, okay, so we have got this inequality that says as follows, which in particular means that okay, 2m is strictly smaller than 6n. So now if every vertex would have a degree at least 6, it will count the edges incident with it. The count will be at least this one, but every edge will be counted twice from both endpoints, and this is a contradiction because we have got the inequality in the second direction. Okay, so that was the proof that probably everybody of you have seen, that every planar graph has got a vertex of a degree at most 5, because if there were 6, I mean, these calculations will go wrong. But the other thing here, I mean, I did it for connected graphs, and of course, like, I mean, you just take a disjoint union of connected graphs and you have got the same thesis here. But I want to show a second proof, which is essentially in its guts the same proof, but has got a different formulation, and this formulation is somewhat useful for having this type of proofs, but more complicated. Okay, and the second thing is via something called discharging, and this is really using like double counting argument of Euler's formula in a better presented way, and that makes it easier to develop more complicated double counting arguments. So this is called discharging, what you can think of about like moving some potential on the graph and like doing some double counting, but let's think discharging. So there are some like charges in the graph, and the process is like we put some charges in the graph and then we move them around and we see how it ends up there. So let's do the simple example here. So we usually, when we set up the charges, we usually want to use the Euler's formula. And the usual way of doing it is just to put some positive amount on every face and vertex and the same negative amount on edges. And by Euler's formula, which was again n plus f minus m equals 2, if you put the same amount on each vertex and a face and negative this amount on every face, on every edge, then the total charge will be like slightly positive. It will be like just this 2 multiplied by the amount, like twice the amount you put on every vertex and a face. Okay, so that's like what we do start from, and we'll use the fact that the total charge in the entire graph is positive. That means that if we move and we reshuffle these things, there will be always some object in the graph that has got a positive charge, and that will give us some things. Okay, and now let's do some reshuffling, and here the reshuffling is simple. We send one each vertex, sends one to each of the incident edges. Okay, sends one to each of the incident edges, and every face takes its charge and discharges equally. So this sends one, and this discharges equally to each of the incident edges. Okay. Okay, so this is the move. So it's not very complicated. We'll see a complicated example in a moment, but let's make an analysis what happens here. Okay, let's make an analysis. And okay, so what happens with on faces? So faces are the simplest one. Faces got completely discharged. I mean, we did it, and there's no rule that gives a charge back to a face. So the faces got charge 0 at the end. Okay. The interesting thing is what happened on edges. Okay, an edge started with -6. It got 1 from each of its endpoints, and it got something from the faces. And now, I mean, the previous proof to use the fact that the face has got at least 3 edges. We also need to use it somewhere here. Right? It would be worrying if we didn't use it. Fact. So now we use it. Face has got at least size at least 3, which means that it sends at most 2 to each of its edges. Okay, a face of size 3 sends 2, size of size 4 sends 1/2, and etc. Okay, so it gets at least 2 from here and at least 2 from here, which means that it ends up non-positive. Okay, if an edge has got size 3 faces on both sides, it will end up with 0. If any of these faces is larger, it will end up below 0. Okay. Well, that means that there needs to be, okay, so edges are all non-positive, faces are discharged to 0, but the total charge is the same, and we just moved around some things. So the charge needs to stay at some vertex, okay? There needs to be a vertex of positive charge. But what the vertex does, I mean, the vertex starts with +6 and then sent 1 to each of the incident edges. So the end is 6 minus degree, ends up with 6 minus degree. So a positive guy is a guy of degree less than 6, period, end of the proof. Okay. Yep. So that was like, let's look at the big glance of this thing. This was like in combinatorics, this was like the same arguments we used in proof 1, but this was somewhat like better presented or more like explicit double counting argument than in proof 1, where we're actually like saying, hey, we do this charge, we do this moving, and then there needs to be a positive charge, and the place with positive charge by analysis is exactly the place we were looking for. Okay, so the positive charge places are the guys of the guys of degree at most 6. Okay, the guys of degree at most 6. So this is the simple one. So I want to show you a second example of a discharging argument. That's actually the second example of a discharging argument. That's actually okay, that actually more complicated and maybe actually more, I mean, you'll see something. Okay, so the second example is a theorem saying that, hey, if I have a planar graph and I don't have guys of degree 2 or 1, so I could minimum degree 3 in a planar graph, then I actually have got a vertex and an incident face such that the degree of the vertex plus the length of the face is at most 8. Okay, so actually you can see that like this minimum degree 3 is needed here because otherwise I could put a lot of degree 2 guys everywhere on every edge and every face will be super long, so that won't be true any longer. But I mean, yeah, so I want to prove this type of statement, which is a bit different statement than what we had on the previous slide. Okay, actually it's slightly more general, but let's see how it goes. Okay, Okay, so we start as before, but let's double the charge. I mean, of course, I mean, you can, I mean, it would be easier just to have full integers in what we proceed later. So let's double the charge. We do exactly the same thing as before, like put the same amount on every vertex and face, negative amount on every edge. And from earliest formula, the total is like a slight positive constant. Okay, like twice the amount on every vertex, face, and edge. Okay, so this is our starting. And now we are going to do discharging, and the rules will be, yeah, there was a question in this chat, sorry for that, that the length of a face is number of edges around it. Yeah, if a face, and this is like important is that if you have got, maybe this is an important remark, if you have got a picture like that, okay, actually in this, then I mean, if you have got a picture like that, then this face will have got length 7. Yeah, I mean, it's like you do a walk around the face and you count how many edges there are. So this guy actually will be counted twice. And if you do this one, this will be actually length 10, because I mean, this edge will be counted twice. This one will be counted twice on the walk around the face. Okay. Thanks for the question. Yep. So let's wipe out these pictures and let's okay. Sorry. So let's do the discharging rules. So we have got edge. Okay, every edge fence. So what we want to do, we want to like discharge. I mean, we want to like first make this zero the edges. So zero the edges. It will like a bit simple. Like every, I mean, an edge is incident with 4 objects, 2 vertices and 2 faces, and this edge just takes 3 from each of them. Yeah, this is rule 1. Just every face sends 3 to each edge, and every vertex sends 3 to each edge. Okay, and this is like, this makes edges 0 here. Okay, and now we also do extra things. So this is the main thing we do, but we do extra things for degree 3 vertices and length 3 faces. Okay, there's a one thing that you can observe in this proof, that vertices and faces are sort of symmetric in this proof, because I mean, they're like, instance in this theorem is properly like the graph and the dual of the graph, if the dual planar of the graph, they're really like symmetric in this proof. So yeah, but let's do the things for this. So if you have got a degree 3 guy, it additionally sends +1 to each of the faces. Okay, and the length 3 face sends +1 to each of the incident vertices. The intuition is that, hey, if there was a vertex of degree 3, it sent already to the edges 3 times +3, but it still has got 3 remaining, so it discharges to the neighboring faces. And the same with a face. If a face was of length 3, it still, after the first step, it still kept charge free, so it discharges to the incident vertices up there. Okay, and the intuition of the proof, we just make a formalize, is that, hey, if there is like okay, so a thing of positive charge needs to be something that, okay, because now in this thing, I mean, everybody discharged all his charge. Yeah, edge gets zeroed, and all the degree 3 vertices and degree 3 vertices and length 3 faces, they still have got charge free, so they discharge. And now something end up with a positive charge after all this thing, and we need to like study this object. And the point is that it must be a low degree vertex with a small face nearby, or a small degree or a low length face with a small degree vertex nearby. But let's do the formal analysis. Okay, so the formal analysis is that if something has got length at least 6, it has got no chances of getting a positive degree, a positive thing. So let's like, the point is that, hey, in this step, I mean, a high degree vertex or a long length face, it discharged so much that it's so below 0 that it hasn't got chance to get equal in the end. Yeah, because here the guy started with +12. Okay, it discharged like the number of edges around it times 3 in the first step, and then best case it got 6 back. So best case, all the incident vertices are degree 3, and they send 1 back, and they send 1 back and 1 back, or send 1 in the last step up there. Okay, So the point is that guys of length at least 6, they have got no chances of getting positive in the end. And a symmetric guy, face of length at least 6 and vertices of degree at least 6 is a symmetric argument. I mean, they discharge it so much to the neighbors that even with this +1 sending here, they have got no chances of getting above 0 in the end. Okay, so let's look at the other guys. So the other observation is that let's look at the face. The argument for the vertices metric. Let's look at face. A face of what happens to a face of size 3? Well, things of size 3. Okay, so face of size 3. Well, it sent +3 to the edges, and then it sent +1 to the vertices. So it discharged completely. Okay, so the only hope when a face of length 3 could get positive in the end is that actually it got back +1 from one of the incident vertices, which means that it has got a neighboring vertex of degree 3, and we are more than happy. There's a face of length 3 plus a vertex of degree 3 nearby, and we have got 6. We have got 3 plus 3, and we are super happy. Okay, and a symmetric argument holds for a vertex of degree 3. Yeah, I mean, here faces and vertices are symmetric itself. Okay, so what happened? Okay, so this is like the first thing. So what happens with a face of size 4? Well, this is exactly the same. Well, the size of size 4, I mean, it discharged +3 to all the neighbors, so it got 0. Okay, to all the neighboring edges, it got 0. So if it got positive charge, it's only because there was some vertex who sent back +1. Okay, and this is a vertex of degree 3. So there's a face of size 4 with a vertex of degree 3 nearby. We are done. Okay, the other case is a face of size 5, and this is the same. It sent +3 everywhere. It sent +3 everywhere. So it ended up with -3. So the only hope for it to actually be positive is that actually 4 out of these 5 vertices, or all of them, but at least 4 of these vertices send +1 back. Okay, and that means that it has got not only 1 but like 4 vertices of degree around it. So this thing is still happy. So this inequality is still happy if any of these 4 vertices. Okay, and so this was for a face that has got positive face, and the vertex thing is symmetric. You just replace all the faces with faces and faces with vertices, and the argument is completely symmetric, so I won't repeat it. Okay, so that was some sort of double charging argument where we're like sending things around and like proving that like the structure was the same. Yeah, we put some charge, we moved it around, and we looked at an object that has got positive charge and said that this object and maybe the or neighborhood of this object is exactly what we wanted in the thesis of the statement. Okay, but designing charging like this discharging rules, this is quite a skill, and we'll actually look at it in the tutorials. There are a few examples in the tutorials, and hopefully there will be some example in the homework and about like finding good discharging rules here. Okay, so that's the thing I wanted to show you something, and we'll see more examples in the tutorials of this type of thing. Please keep in mind this discharging technique will sort of handle wavy, say about it later in the four-color the four-color theorem. Good. So I'm going further. Yeah. So as I said, I mean maybe just put it. I put it here explicit. Like discharging is a popular technique for proving something like okay, a graph is usually planar, but some of them not. Actually, we have one example on the tutorials with arbitrary graphs, not planar graphs, and that there's some local structure, and there's sometimes very often these statements are complicated, and we see in four-color theorem that sometimes it's just like a long list of local structures that are fine. We designed something and we want like a long list, we have got possibly a long list of structures that are fine with us. For example, there are structures from which we can carry on some inductive steps, and we are proving by discharging that one of these always appears in our graph. Okay, and this is like discharging is really like a clean way of formulating double counting arguments, which are particularly useful in planar graphs because of the Euler's formula. Okay, so I put here a few examples I found recently. Like you can prove, and this is not non-trivial. In this same setting we had previously, that planar of minimum degree 3, you can prove that actually two guys there are two guys neighboring with the sums of degrees at most 13, which is quite an untrue statement. It was actually a homework on the previous edition that not necessarily planar, but maximum average degree at most 3. So like any subgraph has got the average degree of vertex less than 3 in any subgraph. So there's a vertex of degree 2 in any subgraph. That actually there's like 5 choosability and something called acyclically. So even any 2 colors induce a forest. Okay, so you can actually prove something like that. And actually the degree 5 thing, you can actually prove that planar graphs have not only a vertex of degree at most 5, but you can also, augment this argument that there's a vertex of degree 5, and if you look at his neighbors, there are actually at most 2 guys of degree more than 12 or more than 11. Okay, so this is something you can actually squeeze out of the first argument. And for example, another argument, I think it is theorem of Borodin, is that if you have a planar graph, embedded planar graph with minimum degree 5, so like there are no 4 vertices or whatever, minimum degree 5, then there's actually a triangle face. If you sum up these degrees, these degrees are at most 17. I mean, you can prove statements like that with more and more complicated discharging rules. Okay, good. So this is things. So now I want to leave the world of discharging for a while, and I want to go to the world of choosability for a moment, and actually spend a few minutes, maybe a bit more, on proving Thomassen's theorem. But before we go for the Thomassen's theorem, I want to go for the coloring graphs. So we proved that every planar graph has got a vertex of degree at most 5. And planar graphs are closed under vertex and edge deletion, which means that this is something that we call degenerate. Like any subgraph has got a vertex of degree at most 5. Okay, so planar graphs are 5 degenerate. That means really that you can take a vertex of degree at most 5, delete it, take another vertex of degree at most 5, delete it, take another vertex of degree at most 5, delete it, and have like a sequence of these guys. Let's say the last digit guy is EVN, then VN minus 1, etc., and you end up with an empty graph in the end. And like every guy, once you delete the guy, it has got at most 5 neighbors in the guys that are remaining. Okay, so you can actually order the graphs so that any guy has got at most 5 neighbors among the earlier guys in the order by this process. And this is like an obvious way of coloring the graph. Yeah, I mean, if you want to color this graph with 6 colors, you're just coloring in this order, and whenever you look at the next vertex, he has got only 5 colors used in his neighbors, so you can put, there's a free color for this guy, and you can just greedily color the graph. Okay, you can also phrase it as an induction. Yeah, I mean, you remove the vertex of degree at most 5, color the rest by induction step, and put the guy back, and there are like 5 colors the most used among the neighbors, so you have the 6th color for the guy, and you're happy. Okay, so this is like 6 coloring, but this is something that was known in the 19th century. It's attributed to Hewitt, but yeah, I think it's attributed to Hewitt. I'm not really sure about exactly. But this, but there's just like I think Hewitt published or spelled out a proof for probability using ideas of Kempe, but Kempe published incorrect proof for the 4-color theorem earlier. And he used these arguments to show that actually there's a simple argument of proving 5. But let's look at this. Let's look at this. Let's look at this proof. So, well, if you are having only 5 colors? What breaks down? If you're trying to color the planar graph with 5 colors? Yeah. So remember what we did. Let's think of the following. We are doing by induction. We are taking the guy of minimum degree. This degree is most 5. We're removing it, using the induction to color the rest, and putting the guy back and trying to color it. Okay. So if this guy got degree at most 4, okay, well, there are only 4 colors used at his neighbors, so there's always the 5th color for this guy. So the only problem is that we have got this guy that we are putting back, and we colored the rest from the induction, okay? But these neighbors have got really 5 different colors. I mean, without those of generality, there are around 1, 2, 3, 4, up to 5, okay? So this without the generality, these are like the orders of the, there's like the colors around this vertex in the plane embedding, and now we don't have a free color, so we are maybe like in a difficult position. And now the main idea of Kempe is to actually, hey, let's try. So let's try to recolor this graph, and the point is as follows. So let's try to change this color to 1. Okay, let's try to change this color to 1. Well, but that can break something. It may actually have some neighbors of color 1, but maybe let's change these colors to 3. Okay, and propagate this. So what we're really doing, we take this coloring C, and we take the look at G of C to minus 1 of 1 and 3. So we look at the graph colored 1 and 3, and we look at the connected component that contains this vertex. Let's call this vertex V3, and flip colors 1 and 3 inside, and flip 1 and 3 inside this connected component. Yeah. So I'm taking the graph. I'm looking at the only colors 1 and 3. I'm looking at the connected components of the colors 1 and 3. I'm taking one of these components and flipping colors 1 and 3. Okay, and that's a valid operation for a coloring. That's like an operation that somehow like change one coloring to another one and gives some like way of transforming, like fixing a coloring. Okay, fixing coloring. Okay, so we did it here, and maybe we're happy. Okay, this guy changed to 1, and so we can use color 3 in the middle. Okay, that's good unless this whole propagation went around and actually flipped this guy to 3. That could have happened. Yeah, I mean, we look at colors 1 to 3, so something flipped, and maybe this guy actually flipped. So there was actually some connection 1, 3, 1, 3, 1, 3, that connected these two guys. Okay, and that would be bad. So we flip, and we essentially flipped 1 with 3, and we are still in a bad position. But now comes the super important observation. We are in a planar graph. We haven't used planarity so far. Yeah, I mean, we shouldn't prove that all graphs of we shouldn't that easily prove the fact that graphs of minimum degree 5 are 5 colorable. Okay, so well, the observation is that, hey, but now if we do exactly the same but with 2 and 4, so we look at G of C to minus 1 and 2 and 4. So what we really do, we take this guy and recall it 4 and propagate. Well, now it cannot happen that it bumps up here, because these two things would need to intersect somewhere, and one of them has got colors 1 and 3, and the other has got colors 2 and 4, so they don't intersect. Like in a sense, this red component here separates 2 from 4 in this 2 and 4 components, so they need to be in different connected components. So now flipping here 2 to 4 and propagating won't change this 4, and we are happy we have got color 2 here. Okay. So that's like the crucial idea, and this is something that will come up a few times today in the second half of the lecture. Okay, and that this idea of like actually this using the planarity this way, and this like recoloring the component is sometimes called the Kempe chains. This propagation of like flipping a color, then flipping the neighbors back, then flipping the neighbors of the neighbors in this direction, etc., etc. This is often called Kempe's chains. And this because it was described by Kempe in 19th century as like in his attempt to prove the 4-color theorem. Okay, so this is the proof here, and it's actually important for the technical reasons. But let's go to the Thomassen's proof that planar graphs are 5 choosable. So we are going to actually prove more about planar graphs. The first proof was quite simple. Now we are going to show you a similar simple algorithm. Actually, planar graphs are 5 choosable. So not only you can color them with colors 1 to 5, but you can color them if everybody have got different leads up there. Yeah, and this idea with the Kempe chains doesn't really work that well. Doesn't really work that well with the list, because this flipping, I mean, these guys may not have got the thing to flip to on their lists, and there are like various problems. So this Kempe chain argument doesn't really work that well in you look at choosability, not colorability of the graph. So there's a proof of Thomassen. He solved something that was conjectured for a long while, and this is a beautiful example of one of the paradigm that if you carefully craft the thing you're pushing through induction, everything goes like super smoothly and there's nothing to prove. So the entire proof really is to precisely formulate what will be pushing through induction. We're proving something slightly stronger than 5 choosability, but the slightly stronger will be so super calibrated that it will like push itself without any effort through the induction. Okay. So let's see what slightly stronger statement of 5 choosability will be used in pushing through induction. So I looked into Thomason's paper. It's really one paragraph. I mean, it's like the statement and one paragraph proof there. We'll be doing a bit more than one paragraph. I mean, that was a bit too concise, but let's go. Okay. We'll be looking at the graph. So the first observation, this observation that will happen a number of times in the second half of the lecture, is that adding edges only makes our life harder as long as the graph is still planar. So as long as the graph is still planar, you can add edges, and coloring is even harder. So you can assume that the graph is triangulated. So every face is triangle because you can always add things to the triangle. Actually, we'll be doing something different and not triangulate everything. We'll leave the outer face. So we'll assume that our graph actually has got a cycle as an outer face, because if you have got something like that, I mean, okay, so this is actually, we'll be doing cycle. I mean, we'll be in a moment. We'll be I mean, you can, if this if this happens, you can always add also this edge up there and have a cycle outside. So we assume that outside there's a simple cycle. Outside there's a simple cycle, and everything inside is triangulated. So everything inside, every face inside is a triangle, but the outer face may be longer. Okay, and there's a cycle. And on the cycle, we have got two guys with already assigned colors. So this guy will be already, I don't know, gray, and this guy will be already orange. Okay, and the lists will be of size 3 along the boundary, of size 5 inside. Yeah, so this is like a bit stronger statement. Okay, we're assuming the graph is triangulated, but that makes our life even more difficult, except for the outer face. And we'll assume that there are two neighboring guys on the outer face that already have their colors, and our guys on the outer face will have got lists only of size 3, not 5. Okay, so this is the stronger statement. This is the stronger things, but it will work super smoothly through the induction moment. Okay, and we want to say that this graph, you can always choose the colorability in this type of graphs by induction. Okay, let's do the base of the induction. The base of the induction, well, what's the smallest graph that looks like this? Well, this is a triangle that this guy has a color orange, this guy is color gray, and this guy has got a list of size 3. 1, 2, 3. Okay, so one of these colors may be orange, one of these colors may be gray, but there's a third color, and we are happy. We can color the graph. Okay, so far so good. Let's do the induction hypothesis. And the induction hypothesis means that, okay, I have got a large graph, and there are these two guys that are colored gray and orange up there, and I mean the guys outside has got size list size 3, inside has got size 5. Okay, there are two cases that we need to distinguish. The first case, that actually there is this outer cycle has a chord. So there are actually two guys here that are connected by an edge which is not on a cycle. Okay, this edge connected. Okay, so there's a chord like that. So actually, so this orange-gray part needs to be on one half of the cycles. I mean, one of the endpoints can be this orange, but these are two adjacent guys up there. So they're like either on the left side of the cycle, on the right side of this upper cycle. Okay, so what we do, we apply the induction first here. Okay, so the induction hypothesis says, okay, this is a smaller graph. This part is a smaller graph. So you can color it. Okay, this guy has got size 3. These two guys are pre-colored. Everything is fine. Everything is satisfied. So you can color these guys. So you end up with actually this guy colored, say, green, and this guy colored magenta. And now this is the moment, the first moment where you say, hey, but this is excellent. Now this second part, again, exactly looks like our picture. We have got the outer face with two guys pre-colored. Okay, these are called magenta and green, but we don't care. And the other guys have got lists of size 3, inside guys have got lists of size 5. We're happy. So this is the moment when we really like use the fact that this induction gives us two pre-colored guys on the boundary, because I mean the first part, this is the information that the first part forced on the right part, because it's already pre-colored these two guys up there. Okay, excellent. So the induction like just works smoothly. So let's go to the second case. I mean, this chord might not exist. So there's no chord. How does this picture look like? So let's draw now a big figure. There was the orange guy and the gray guy up there on the boundary. Okay. And now comes the main trick. The main trick, I mean, the main idea is to look at the next guy on the boundary. Like this is the next guy on the boundary up there. And let's look at his neighbors. Okay. He cannot have a chord because that was case 1. So actually he's got the next guy. He actually has got this guy as a neighbor, and he may got a few neighbors inside. Okay. This was a triangulation, so there are actually edges looking like this. Okay, good. And now our idea is to actually hide this guy. So like this guy, we want to hide it for a moment. Okay, we want to hide this guy and apply the induction for the rest, and then put this guy back. But this won't work that easily. I mean, because he has got list of size 3. Okay, he has got list of size 3. Yep, actually, this list even may contain an orange color. Okay, maybe a few other colors. We don't know which ones. Okay, maybe a few other colors. And well, then yeah, so that makes and maybe these colors will be quickly used by these neighbors because we don't have a bounded number of the neighbors here. Maybe, but the power we have here is that these guys have got list of size 5 because there were no colors. So these guys are inside guys. Okay, this guy has got list of size 3, but this guy has got list of size 5. So we can actually subtract and we can actually hide some colors from their lists. Okay, and this is what we are going to use here. So this guy may have orange, but apart from it, it has got 2 other colors. Say it has got magenta and green inside. Okay, so we take 2 colors that are not orange. We take 2 colors that are not orange, and we remove green and magenta from these 2 lists, from this list inside. So we take these guys here, okay, and we remove the green and magenta. Green and magenta are just 2 colors for this guy that's not orange. That's not the color that the neighbor of this cycle was colored with. Okay, so we hide these 2 guys from these colors. We reserve these colors. Hey, don't use these colors because this vertex may need them. Okay, because we cannot. I mean, the problem here is also that we cannot restrict the list of this color. He's got list 3, and we cannot do any more because the induction requires list of size 3. So we cannot do anything with that. But we can hide the green and magenta from the list up there. And now what happens? Okay, induction now works. It has got 2 guys of degree 1 and these guys of 3 colored, and these guys have got list 3. Excellent. So it colors the graph. Okay, it uses orange here. It cannot use green nor magenta here because we remove these guys from a list. It may use green here, or it may use magenta here, but only one of them, which means that the second one will be left for this guy. Okay, let's repeat. We hit the green and magenta from the guys there. Okay, which means that from the induction hypothesis, the coloring we have from the induction hypothesis, from the list of this guy, the orange may be used by this guy, but neither green nor magenta will be used by the guys here. This guy will use green or magenta, maybe, or maybe something else, even better. But the second out of the pair green and magenta will be used, will be left for this guy, and we are happy we can extend the coloring. Okay, so this was like a very delicate use of the fact that there's a drop from 5 to 3 if you go to the boundary. And I mean, I found it super smart and super tricky how to use it, but it makes the 5 choosability proof go super easily. And okay, we started discussing this theorem less than 2 minutes ago. Okay, good. So this is the theorem of Thomason for the 5 choosability. And unfortunately, the 4-color theorem is not that simple. So let's try to spend the remainder half an hour of the proof on discussing some parts of it. Okay, so this was 5 choosability of planar graphs. Let's go further. So as I recalled, we had this theorem this was proved by Appel and Haken, and then the simplified proof for Robinson, Sanders, Seymour, and Thomas. Okay, so let's try to prove this theorem. So we're doing induction again. The induction is sometimes better phrased, and this is one of these cases. take the counterexample of minimum number of vertices and then reach a contradiction. Yes, so we take the next graph and we assume that all smaller graphs are actually four-colorable, or smaller planar graphs are actually four-colorable, and we want to look at this, the guy with minimum number of vertices that's not four-colorable. And okay, so what we can say about this guy? Well, I want to say that there's minimum degree 5 in this graph. Okay, so if there's a guy of degree 3, we could have, or less, we could remove it, color by induction, and put this guy back, and we are happy. The point is that the Kempe China argument will also work for the guys with degree 4. If there's the guy of degree 4 that we are trying to put back, but he's got 4 guys of 4 different colors, that may happen, then actually you can again do the Kempe China argument. Yeah, you can take the 3 and try to recolor it 1 and then propagate. And okay, it may actually recolor this guy to 3, but again, now recoloring 2 to 4 cannot reach recoloring here to 2. Okay, you can't have this both and once. So the Kempe China argument would work here as well. Okay, so if the guy of degree 4, you can remove it, color the by induction, and try to put it back. And if there are 4 different colors, then one of the Kempe recolorings would actually work and save you the day. Okay, so we have got minimum degree 5. We can actually do exactly the same trick as before, namely, I mean, if you add an edge keeping it planar, I mean, make our life harder, we can actually triangulation. And we're actually coloring the triangulations. Current triangulations here will be useful later in the chapter. And what we can also assume is that every triangle is a face. What do I mean here? I mean here that I cannot have a triangle in this graph that actually has got something both inside and both outside. So, okay, so there's no triangle shown up there. Why? Well, this is reasonably simple. So if I have got such a triangle, call it V1, V2, V3, let's call G1 the graph inside, let's call G2 the graph inside, including the cycle. So the cycle, so like G1 intersection G2 is the cycle V1, V2, V3. Okay, so let's call it so. By induction hypothesis, both G1 and G2 are four-colorable, and now you can merge this. I mean, okay, but the coloring of G1 just colors this with 1, 2, and 3 without any, just colors this with colors 1, 2, and 3, and the coloring of G2 colors it a few different colors, so you can just like permute the colors one of them and glue them together, and you have got the color of everything. Okay, so I mean there cannot be like any separating recycle because by induction happens to color the 2 sides and just glue the colorings of the and you're happy. Okay, so there are no like separating triangles in this counterexample. But we can say more, and this is a good insight actually of Robertson, Sanders, Seymour, and Thomas. We can say that actually there's no separating for cycle. Okay, and this is a bit more complicated, yeah, because the previous argument, okay, so let's say that we have got this 4 cycle, and let's say everything inside is G1, everything outside is G2, and G1 and G2 includes the cycles. This is like V1, V2, V3, V4, and G1 and G2 include the cycle. Okay, so you are tempted to say, let's color G1, let's color G3, G2, let's color G1, G color G2, and if you can permute the colors on the boundaries so that they actually match, then you're fine. So you shouldn't be able to do it. And the proof but in the triangle, say you just said, okay, but the triangle needs to have got 3 different colors, so you can always like permute the colors so that these colorings match with each other. But here it's no longer true. I mean, the colorings may be like 1, 2, 3, 4, but it can be like 1, 2, 1, 3. It can be 1, 2, 1, 2. So they not necessarily match each other. Okay. But there's a good trick of doing it. Namely, you can always draw this edge you can always draw this edge, or you can draw this edge. Okay. So let's say that we are looking at G2. But we are adding edge of V2, V4. Okay, so we are taking the graph outside, but we are adding the edge of V2, V4. Okay, it can end up with coloring that just puts colors 1, 2, 3, 4, or it can end up with a green coloring that puts colors 1, 2, 1, 3. Okay, up to the names of the colors. I mean, you can permute the colors. But the point is that if you ask the inductive hypothesis, okay, what's the coloring of G2 plus the edge V2, V4, it can return like either the coloring that puts all 4 different colors on these vertices, or puts the opposite guys equal, the V1 and V3 equal, and other two guys to equal. I mean, it has got like 2 options of like what's the interface of the coloring returned. Okay. And now what we can do in our proof, we can actually ask for like, I mean, there are like 4 questions we can ask here. We had this 4 thing, and we could ask this edge or this edge. Okay, and we could do this was for G2, and we could add the same question for G1. So we could ask this edge or this edge to G1, and like sort the 4. Okay, what's the coloring now? Okay, what's the coloring? Okay, so we have got this 4 questions we ask. They're up there. Okay, and all these questions returns a coloring, which is either a coloring like all 4 guys are different, or the non-adjacent guys have got equal colors. There are like 2 different types of colorings, and we cannot match them easy. and now let's look what we can match with each other. Okay, and now the thing is that, okay, if one of the colorings of G1 returned colors 1, 2, 3, 4, regardless whether this was this edge or this edge, and if one of the colorings of G2 returned 1, 2, 3, 4, 1, 2, 3, 4, then we are happy. We're just gluing this coloring. Okay, maybe the names of the colors are different, so we need to permute them, but whatever. Then we are fine. Okay. So the only problem is that if one of these graphs, say G1, if this one returned coloring, actually, if you think about if this one returned coloring, so this was with this edge, yeah. So this returned coloring, say 1, 2, 3, 2, okay, and this one, this was this returned coloring 1, 2, 1, 3. Okay, so there's only a problem if one of these things returned like in both variants returned with 3 colors, with a repeating color up there. Okay, but now the observation is that, okay, but now if you look at what happens with G2, if you add this chord, and if it also returned 1, 3, 2, 2, then you're happy because this thing matched this thing. Okay, I mean, they're the same. I mean, you can, okay, maybe permitting colors, but they match. And also, if this guy, if this thing for G2 returned 1, 1, 2, 3, then this thing matches this things, and we are also happy. We can color the entire graph. So the only remaining case is that actually on one side you have got 2 colorings. In both cases, you got 2 colorings for repeated color, and in the other case, you got both colorings without the repeated color. So actually, it's actually really here, both things is 1, 2, 3, 4, and 1, 2, 3, 4. Okay, 1, 2, 3, 4. So this is the thing when we cannot match. But now, Kempe chains come to the rescue. Okay, Kempe chains come to the rescue. You look at this graph. Okay, and now you take your favorite color, say now orange, and you try to recolor 3 to 1. Okay, and propagate it inside the graph, and propagate inside the graph G2, and propagate inside the graph G2. Hey, but okay, this may happen. It may actually recolor 1 to 3 or not. If it propagates and recolors 1 to 3, that means that recoloring 2 to 4 won't recolor 4 to 2. And so the observation is that using Kempe chains, if you get the coloring 1, 2, 3, 4, you can always recolor it into one of the repeating coloring. You don't have a control into which one. You don't have a control if these guys will be repeated or the orange guys will be repeated. Yeah, you don't have the control over the orange Kempe chain will succeed or the magentas Kempe will succeed. But you have got the property that if there is a coloring of G2 with 1, 2, 3, 4 on the cycle, then there's actually a coloring either 1, 2, 1, 3 or 1, 2, 3, 2. Okay, there's one of these 2. We don't know which one, but one of them exists. But that's perfectly fine because that means that on the red side, on the G1 side, I mean, you have got both of them. You have got both this and this, which means that you will be fitting one of them. Whew. That was more complicated. but successful. Okay, so just on a high level, if that wasn't like all the details were not interested, at high level, what we said is that we use the induction inside and we use the induction outside of this place with this extra cord added, because we couldn't just to force. So yeah, with this extra cord, the actual coloring from the induction can be of one of the two types, can be either use all 4 colors on the cycle or repeat the color like perpendicular to the cord, repeat the color there. Okay, and now we looked which guys match to each other, and we observed that the only problematic case is the case when on one side you have got always repetition and on the other side you got never repetition. In both cases you got never repetition, but then Kempe came to the rescue and said that if you have a coloring with all 4 colors, then you must have one of the colorings with repetition, because the Kempe give one of such colorings. You don't know which, but one of them is given. So this is interesting. But it turns out that actually you can prove more. But you can actually also kill 5 cycles, except for one special case, which we'll do in the next 15 minutes. But to go there, we need to change the paradigm a bit. So to go there, we change the paradigm a bit, and we actually will be coloring now edges. So the observation is that we're using a lot of symmetries of these colors 1, 2, 3, 4. And we want to somehow like eat some of this symmetry, or like embed some of the symmetry in the problem so that there are less cases to use. And the observation is as follows: if we have got, we are now strongly relying on the fact that we are using triangulations. So if I have a triangulation, okay, I want now to label the edges with 3 colors ABC. So remember that previously we have colors 1, 2, 3, 4. And now I want to label the edges with colors 1, 2, 3, ABC. And the point is that the lemma observation, this is observation that appeared in many papers on the 4-color theorem earlier, or 4-color conjecture earlier, is that actually it only makes sense. I mean, instead of 4-coloring the graph, we want to 3-color the edges such that every triangle has got all 3 colors. Okay, so every triangle has got all 3 colors. And why this is true? Well, the intuition, I mean, I don't want to prove the super formal, I mean, to prove all the ideas of the proof, but in one direction, if I have got a triangulation, that's like, that's properly colored. So let's, well, the 1, 2, 3, 4, I wonder if this would be a good example. 2, I mean, I should succeed here in the end. No, I put it wrong. 1, 2, 3. So here I should put 4. Sorry for that. I didn't prepare an example here, and that was apparently a mistake. So this should be 2. No, this shouldn't be 2. This should be 1. Sorry for that. This should be 1. So this should be 3. Yeah, I managed to 4-color. As you see, it wasn't easy. Okay. And now the point is that you color the edges 1, 2, and 3. I mean, there are like 3 pairings: 1, 2, and 3, 4, 1, 3, and 2, 4, and 1, 4, and 2, 3. And these pairings get 2 different colors on edges. So like all 1, 2 get color A, and 3, 4 get color A. Okay. All the 2, 3s get color C, and 1, 4 get color C. Okay. And the 1, 3, and 2, 4 gets color B. 1, 3, 1, 3. Then I lost something on the way there. This should be A, and 2, 4 should be B, and this should be C. Okay, so we do, and now it's obvious that on a triangle you get 3 different colors, and these 3 edges will have got 3. We got 3 different letters, okay, because I mean these are like 3 different pairings of the colors. And in the other direction, that if you have got the edge coloring, then you get a proper 4 coloring of the graph. It's just the observation that if you start, I mean, okay, the colors 1, 2, 3, 4 are symmetric, so just take a vertex and put some color there, like some color there, and then just propagate along this edges. So like to keep this thing. And the point is that the fact that every triangle is free colorable is exactly what you need. You need to look at stars for a moment. Is exactly what you need so that you don't have any contradiction the way there. That you are actually starting from one vertex that's propagating according to this rule here, like that A means something, B means something, C means something, and it will actually propagate the entire graph. Okay. So this is a sketch here. So we are actually changing the paradigm from free coloring for coloring paragraphs, like free coloring edges of a triangulation, so that every triangle is actually free colorable. I'm put here without the separate free cycles so that I can say about like a triangle, not a face triangle. So I want all triangles to be faces. Yeah, I really want only faces to be like ABC here in the statement. Good. So I changed the paradigm, and now I want to say, okay, now I want to say that in this paradigm, I also have got a notion of a Kempe chain. So the Kempe chain will be like as follows. I start with some edge A on some triangle, and I want to recolor it to B, which means that on this inside triangle, there will be like B guy that I want to recolor to A, and then there will be like another thing whenever like B was recolored to A, so there will be A recolored to B, then there will be some B recolored to A, and it will propagate, and it will be like really chain. Okay, with this edge, if this has got two triangles on two sides, it will go in both directions, but it will really like go there and like propagate one like branch. It will really go like next triangle, okay, another edge flips, then triangle, another edge flips, and the only way it can stop is that it will actually loop back. Yeah, I mean, this process is like defined in both directions. Yeah, in the sense like I'm changing an edge, then like both triangles, I mean, I need to flip something, and this just needs to close in a cycle. This is like the only thing, the only way how it can actually like end up this recoloring. So really like if you're looking just at edges of A and B, it really partitions into like cycles in the dual, and you're just flipping the colors in one cycle. Okay. So this is like, and this that makes this Kempe chain type arguments a bit neater than the previous one. Good. So let's go further. I want to say that they may be separating 5 cycles, I mean, up there, but they can only be of this type. I mean, okay, 5 cycles, okay, they can be 5 cycles that are just triangulated, but if there's a separating, like vertices on both sides, then actually one side, I mean, I allow this picture, but nothing else. These are the only 5 cycles that I have in my graph. Okay, the only 5 cycles that I have in my graph, I mean, okay. So I actually have got the picture. I mean, the thing I want to reach contradiction from is that I have got things. There is some G1 inside, the G2 inside, and both G1 and G2 has got more than one vertex apart from the 5 cycle. There's more than one vertex apart from the 5 cycle. Okay, good. Let's make this definition as before. I mean, exactly what we had before. There's this thing, there's G1 inside, G2 outside, and the guys are called V1, V2 up to V5. And again, we want to play the same game, but to be a bit more complicated of actually like, okay, what are like the traces of the coloring of G2 on the cycle? What are the traces of the colorings of G1 on the cycle, or the restriction of the colorings of G1 on the cycles, and whether there are any two of them compatible? We're trying to look at the compatible guys. Okay, so the obvious thing that we want to do, okay, let's draw this thing. You have this, you have got G2 inside, and remember that G1 was more than one vertex inside the cycle. So the tempting thing to do is to actually draw a vertex V inside, okay, and ask, hey, what's the coloring of G2 plus this vertex inside? What's the colorings of the G2 vertex inside? So you think about this coloring, well, and we are coloring edges, remember, then, well, these 5 edges, I mean, you cannot use 3 times the same label, yeah, because they need to alternate. I mean, you cannot use same label twice in a row because they're triangles. So you can, so the like, it's AB, ABC up to relabeling and rotating. Yeah, I mean, you need to use one label once and the other 2 twice in this manner, and just, okay, you can rotate this picture, you can change the names of ABC, but that's it. Okay, this is the only thing you can do, which means that you have got C, 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 AB here. Okay, what does it mean? That means that actually there is a coloring of G2 such that this cycle is colored CCC, CCC AB. You don't know where this AB is, you don't know the rotation, but the coloring really is like 3 equal edges, 2 different edges. Okay, so there's a coloring like that. So I mean, okay, so without loss of generality, you can assume that there's some like 2 edges out there that you can color AB and the rest C in like G1 or G2 or whatever you want to look at. Okay. So what's said here is that okay, this is like the coloring of the cycles looks like that, A, B, C, C, C. I mean, you don't know the rotation, but set there. Okay. So let us look at the colorings of this type, where 2 edges are of color, 2 distinct colors, and 3 other edges are like 3 edges are equal and 2 other colors. Okay. So let's look at the colorings that use colors A, B, C, C, C. Okay. Let's look at the colorings and let's look where the edges A, B look like. Okay. So you can think of it that there's actually like, okay, I have got these 5 edges on a cycle, okay, which are call them E1, E2, E3, E4, E5, okay, let's call them. And that's like, okay, for which guys, if I color this guy A, this guy B, and this guy C, the remaining C, that I can actually extend it to the entire G1 or extend it to the entire G2. Okay. Okay, and this is a coloring like of G1 or G2, say G2. We are looking at G2 here. I think actually, let's look. I think it will be, okay, it doesn't matter. Let's look at G2 here. Okay, so we're looking at for each ones. And well, now, okay, we just proved previously that for some rotation of 2 consecutive guys, you can make the coloring. But the point is that you shouldn't be able to make for all rotations. Yeah, if you can do it for all rotations, then you look at the G1 symmetrically, and also for some rotation, it's true that you can do A, B, C, 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 and that would actually match each other. I mean, if you can have G1 and G2 with the same rotation, then they match, these colorings can be glued together and you're happy. I mean, maybe with some reliability, of course, but this match and you can color the entire graph. Okay, that means that, okay, if for G1 you can color with some labels being A and B, you shouldn't be able to color G1, or I mean, only one of the G1 or G2 can be colored with this labeling, the same labeling on the cycle. Okay, so if you look at just G2, okay, there are some rotations of like 2 consecutive guys being A and B. That's true because that's what we've proven, but it shouldn't be all of them because the other guy G1 has got 1 rotation being true, and you should have no there. So without loss of generality, let's assume that you can do 1, 2, but you cannot do 2, 3. Okay, so you cannot extend to G2 the coloring where E2 and E3 is A and B, and the rest is C. Okay, but you can do 1 and 2. Okay, that's like I'm just breaking like the naming of the edges symmetry here. Okay, up there. Good. So this is where we ended up here. And now we are using the Kempe chains. And this is the picture that I want to draw here. I want to do this. So let's look at this coloring where this edge, this is edge E1, E2. Okay, when this coloring. So I color this A, B, C, C. And now I want to do the Kempe chain. So let's take the red color. And now I want to recolor this guy into C. Okay, so there will be a triangle with a sky here, which needs to be recolored A, and then this guy needs to be recolored. This guy has got some A that needs to be recolored C, etc. It will propagate, and when it will terminate, so there will be this propagation here, and it needs to end with one of these C edges here. Which one? Okay, which one? Which one? Well. Okay, which one? And the observation is that it cannot end. So let's say it cannot end starting from here and ending in here. Because if we flip the A and C on this chain, then this will get A, this will get C, and we'll have got 2, 3 coloring. A coloring that gives 2 distinct colors here and equal colors here. Okay, so it cannot end here. And the other observation is that this is the planarity observation. The planarity observation is that it cannot end here. Why? Because that means that if we start from this guy, the AC chain, so like again, recolor C to A, recolor A to C, etc., then it would need to end up here. Yeah, I mean, this is the important observation here that, okay, we initially have got letter A here and letter C here, and we're looking at the recolorings A to C, C to A, etc. So you start from here, you end up with one of the C's. So you start with the C's, you end up back in the same place here. You start from here, you end up back, and you start from here, end up back. And this, so this four edges are paired, which guys are connected by this Kempe chains, and this Kempe chains cannot cross. So the pairing really needs to be this guy with this guy, and this guy with this guy, or this guy with this guy, and this guy with this guy. Okay, so these pairings really need to be like respecting planarity. So the only hope for the Kempe chain from here is to actually end with E3 or E5, but E3 would give a 2-3 coloring, which is forbidden. So it needs to end with A5, which means that you actually have got 2-5 coloring. Which means that you actually have got a 2-5 coloring. Yeah. So if you recolor this guy to C and this guy gets recolored to A, you get actually a recoloring that uses for edges 2 and 5 the unique colors, and the other 3 have got 3 equal colors. Okay, that's a corollary, but we have seen how to use Kempe chains here. Okay, so what we know here, we know that 1-2 was yes, and 2-5, we did that 2-5 was yes, and we assume that 2-3 was no, and we actually used that 2-3 is no to say that 2-5 is yes. Okay, let's go further. So now comes the trick. The trick is, so this should be like G1 because we called G, so now we are looking at G1, sorry for that. We're looking at G1, and the point is that, so now what we are doing, so now we had this 5 cycle, and this was V1, V2, V3, V4, V5, and this was E1, E2, F, E3, E4, and E5. And now we are looking at G1 inside, okay? And what we do, we make the following observation. We add this edge and contract it. Okay, so make a graph where we are actually adding this edge and contracting it and observing that this is a triangulation. Because what does it really mean? Now the cycle really becomes a triangle E1, E2, E5 with the edge E3 equal E4 here. Okay, and G1 graph outside somehow. Okay, it becomes really like that, and it still is triangulation after adding the red edge and contracting it. And we can apply the induction. This graph is smaller. Okay, so it produces some labeling of the edges by induction hypothesis, and we can lift back to the uncontracting things, and actually produces a labeling of G1. Well, with this guy, so this triangle needs to get 3 different colors. So it gets color ABC. Okay, it gets color ABC, and this guy gets equal labels, but we don't know which one it is. It may be A, B, or C. Okay, it may be A, B, or C. Okay, this X may be A, B, or C. Okay, so we know that G1. So we know that G1 has got the labeling, A, B, X, 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 X. If you just look at edges 1, 2, 3, 4, 5 in this order, but we don't know which X. I mean, we don't know. I mean, which color is the X? I mean, we don't control it. But let's do case analysis here. Okay. Okay. The point is that, okay, if you get a coloring A, B, C, 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 then this is a 1-2 coloring. It will fit 1-2 in G2. Okay. This is, we are calling G1 here. Okay. Sorry for swapping the guys in the proof. Okay. And the point is that also A, B, 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 C, this is 1-5 coloring, and we this 1-5 coloring, we don't know anything yet here, yeah. But the our observation is that A, B, A, C, this is a 2-5 coloring, and we have got analogous coloring of G2 here, okay, and it would fit. So the point is, the observation is that we must have X equal B, otherwise we have got too much in colorings of G1 and G2, and we are done. Okay. Okay, I will make a slightly longer lecture today. Maybe I'm shortening the next one just to finish this proof here. I'm 5 to 10 minutes before from then, so sorry for that. But let me try to finish here because that makes sense to stop here. Okay. So the observation here is that, hey, the only case where we are not fitting the previous. So the only case where we're not fitting something that we know for G2 is true is that actually X equals B. So we have got a 1,5 coloring of G1. Okay. So the color, so we have a 1,5 coloring of G1, which means that we cannot have a 1,5 coloring of G2. Okay, so again, here should be 1. So the conclusion is that 1,5 is no. That 1,5, I mean, we cannot have a 1,5 coloring. Okay, good. How did we use the fact that we don't have any coloring? We tried to do some Kempe chains previously. We tried to have some Kempe chains from some yes coloring and excluded some case because we couldn't get a 1,5 coloring. So what does it mean? Well, let's look at this 2,5 coloring we obtained on the previous slide. So this was the coloring with this being A, this being B, and this being C, C, C. Okay, and let's start the chain from here. Let's start the chain. It was magenta previously. Let's start from chain to here, swapping it with C. Okay, so as previously, this chain will go and we will end up here or here. It cannot end here because if this would end here, then the chain from there cannot end here. Yeah, so this is like again the planarity. Okay, so the chain from 2, okay, where can it end? The point is that if it, okay, so where it can't end, so this was from H2. If it will end here, okay, it will actually put C here and A here, and this will be a 1,5 coloring. Okay, so actually we obtained that. So this is bad, so this can't happen. So actually the option, the green option is here, is actually this chain ends here. So this became C, this becomes A, and we get a 3,5 coloring. Okay, this is the only option left. Okay, so we got the 3,5 coloring. Good. Now another picture is that we start from the thing we started from the very general when there was A, B, C, C, C. This was H1, 2, 3, 4, 5. And now we started again in this thing, we start the BC chain from here. So we replace this one with C. And where it ends, where the planarity forbids it to end here, because then these guys cannot be connected by a Kempe chain. So it ends with one of this, and it cannot end here, because if this is replaced with C and this is replaced with B, this is 1,5. Okay, so this can't happen. So the only thing that can happen is the green guy, that this actually Kempe chain lands here, and this guy gets replaced with B, and we obtain 1,3. Okay, so we obtained 1,3, 3,5, 2,5, 1,2. This is the guys we already know there are. Okay, there are. And now the final step is to actually look at G1. So we look at G1. So G1 is inside. 1, 2, sorry, G1. So this is H1, 2, 3, 4, 5. These are there. G1 is inside. And we add edges. We add edges incident to the vertex 2. We add edges incident to this. So we add this edge and we add this edge. And this is again triangulation. So this is corable. And now, now we need to do the case analysis to say that actually, like, however this guy is colored, and this is like pretty simple. However this thing gets colored, the coloring will match one of these 4 above. Let's do this case analysis. So, okay, so without loss of generality, let's color this guy C, this guy B, and this guy A. Maybe I should use blue color here. This is A, this is B, and this is colored C. Okay. Then these two guys are colored A or C or CA, and these guys are colored BC or AC. BC or CB, sorry. Okay, because there's an HK, and then G1 gets colored. Okay, this guy is colored up there, which means that we get a coloring. Well, what's the coloring there? It's like, okay, there are 4 places. What's the coloring up there? The 4th place is C. Okay, and now these guys, 1 and 5, are paired into BC, B or C, and these guys are paired into A and C. Okay, they are one of these four colorings. And now we need to check that these are exactly these four colorings here. Okay, if this is AC and BC, this is 1, 2. Okay, if this is BC and CA, this is 1, 3. If this is CB and AC, then this is 2, 5. And I'm running out of colors. And if this is CB and CA, this is 3, 5. So this is this one. Done. I'm done. Okay. This is the end of the proof that the 5 cycles can only have one vertex on one side and the other guys on the other side, or just only edges on one side. I mean, there's at most one vertex on one of the sides of the C5. Period. I got a contradiction here. Okay. So let me wrap up here. So what we proved here, we proved this lemma that there are no 5 separating 5 cycles. And I want now to argue in this like extended few minutes why this is super useful. Well, because now, I mean, the main part of the proof of the theorem is just a discharging argument. It's a huge discharging argument that looks in the paper like this was. These are the discharging rules. This is the picture figuring like all the rules, how you move. So there's a like, okay, I mean, whenever you have got a guy with something, with a neighbor of something, move one vertex. So the discharging rules are actually very complicated. I mean, there's like a few dozens of them. And these are like the pictures, there's a picture of them, but then you have got like a discharging agreement saying that one of a few pages, there are only 2 pages out of, I don't remember, 5 or 6 in the paper, which are all the configurations that you prove that one of them is actually there in the argument. Okay, actually one of them, and then you say that actually you show that actually in these configurations, I mean, in all of them, you can push the induction through. So whatever you have got in the graph, you can push the induction through in this configuration. Okay. So that's how on a super high level proof works. And now how does the previous one works? The previous one works is that you do this discharging and you're drawing like some of these pictures like that. Okay, it's complicated. And you suddenly know that this picture doesn't wrap up. That as long as this picture is quite small, you cannot have like, okay, suddenly some vertex on one side and suddenly some vertex on the other side, suddenly being the same vertex and your head blows up because there are like things bending up and the case explode, because any such wrap up will be a separating 4 cycle or separating 5 cycles, which is excluded by the previous theorem. So the main strength of what we proved here is that when you're trying to draw such a local pictures, as long as the local pictures have like tiny diameter, they cannot wrap up. These are all these vertices are pairwise different vertices when you're like unraveling and saying, okay, maybe there's a new neighbor, etc. I mean, it wraps up after 6 steps, not earlier. And this discards huge number of cases. This is like one of the critical insights of like how Robertson, Sanders, Seymour, and Thomas cleaned up the previous proof. Apple and Haken were really like very heavy on case analysis on like what happens when something crops up. And one of the main contributions of the simplifying from the 90s was to actually understand that you can do a clean proof that we have just seen that there are no separating 4 cycles and 5 cycles are very limited, to actually show, and this actually tames a lot like bending or like wrapping up this type of local analysis of the pictures in paragraphs. This is the end. I want to stop here. Sorry for extending a bit, but I wanted to conclude this proof completely today. Thanks. I'm not exactly sure what we do next week because we realized that, I mean, we squeezed essentially the 2 planned lectures to 1, but that was closer to 1 lecture than 2 of them. So I'm not sure what exactly will be on next lecture, but there will be something interesting. So welcome there. And do we have any scientific questions before I stop the recording?